Good morning, good afternoon, or good evening. This is going to be a full paper work through of Paper 2, A Level, June 24. Now, as with all of these, you should be attempting these papers in their entirety yourself first. If you use any kind of hints or mark schemes before you've had a solid attempt yourself, you lose a lot of the value from doing the questions. Watching someone else get the right idea is much less valuable than forcing yourself to have that correct idea. Saying that, let's start. We're just jumping straight into the multiple choice questions. One of the equations below is the equation of a circle. So things we have to have a squared plus the square, so those two fail, and the radius, the r squared on the end, well, r squared is a positive number, so the end number has to be positive. X squared plus y squared equals r squared style. Question 2. The graph intersects at those points shown there. Shaded region A is 189, B is 64. However, B is below the x-axis, so it's really a negative. So this is the 189, but we're subtracting the 64 rather than adding that area on, which gives me 125. Just double checking because there was a negative 125 and the 253 is from adding them together. So any combination would have given you those four answers. A was positive, B was negative. Solve that inequality. Well, solving quadratic inequalities is finding the critical values, which is solving the equal 0, which is at 1 and 4. And notice that this is a negative quadratic. You get negative x squared if we were to expand it out. Between 1 and 4, we're less than 0. So we want that region and that region. So we want to be less than 1, greater than 4, which is answer 1. Oh, and notice the difference between answer 1 and 2. Answer 2 is actually empty. Nothing is less than 1 and greater than 4. So we should be using the U symbol, not the N symbol. And if we do glance at the other options, the difference was the greater than or equal to 4. We're strictly less than 0, so we have to be strictly greater than 4. It's worth checking with these multiple choice ones why the other answers are wrong, if they are that similar. Use logarithms to solve that equation. Okay, well, I'm going to take Ln because Ln's just my favourite. And using the fact that the power can be brought down. So I brought the x minus 2 down, and I brought the power of 1570 down. If you do try and type that number into your calculator, I think the calculator will give you an error. It's too large. So if we carry on, maybe the easiest is to divide ln 7 over ln 5, and then add 2. And I'm doing everything exact to show the steps very, very clearly. It's a little harder to see the exact steps if everything is horrible numbers, and there's a much greater chance of sign errors, transcription errors, that style thing. Gives you answer to 2dp. Now, does that seem reasonable? That is an awfully big number, but we're trying to match 1500, but with a smaller base number, so we need a larger top number. So 1900 does seem reasonable. Question 5. Given that, differentiate it. So this is going to be a classic quotient rule. Let's set it up. U dash is a simple derivative. V dash sine differentiates to cos. I almost put cos theta out of habit. So dy by dx is u dash v minus u v dash over v squared. over sine squared x. Now I could do some stuff with that. I can split it into two parts, go into cosecs, cots, etc. I could factor out an x squared on the numerator. Question didn't tell me to. Just said find it, so I will stop there. Question 6. It's given that equals 30 and theta is obtuse. That's going to be interesting. If theta is obtuse, that means that sine theta is going to be negative if you consider the... no, it doesn't. Sine theta is still positive for obtuse angles, but cos theta would be negative. So we just need to... That doesn't seem like it's going to come into play then, except just choosing the positive square root at some point. But let's give it a go. If we expand everything out, that seems like the only sensible first choice. Plus 12 sine theta cos theta in the middle, plus 9 cos squared. I'm looking at the other one and I'm already seeing something that's quite pleasant. The middle pair is exactly the same with the opposite sign, so they're cancelling. That was going to be a bit of a problem if not. The 12 sine theta and the 12 sine theta cos theta and the minus 12 sine theta cos theta disappear. Simplifying the rest, that's 40 sine squared plus 10 cos squared equals 30. Just to make it look a little bit nice, I'm going to divide through by 10. And then finally, we wanted sine, so we need to replace that cos squared. Cos squared is 1 minus sine squared, so we've gone down to 3 sine squared plus 1 equals 3. So sine squared, subtract the 1, divide by the 3. Sine theta is plus or minus the square root of 2/3, which, as theta is obtuse, we're going to pick that sine theta equals the square root of 2/3. Sine of obtuse angle is positive, and just in case the examiner is going to be super picky about it, I'm going to quickly rationalize the denominator as well and give it in the most standard looking form. Shouldn't matter, but some mark schemes might be picky about that. 6 marks there, that's quite generous for what we've done, but we have done quite a lot. On the first day of each month, Kate pays £50 into a savings account. Interest is paid on the total. The interest rate is 0.2. At the end of the month, we have TN. She correctly calculates T1 and T2. So T1 we increased by 2%, 0.2%. T2 we put 50 quid in and then increased, and she just substituted T1 in. Show T3 is given by that. Well, T3 is T2 plus the 50 quid that we put in at the beginning of the month, increased by 1.002. So then we take the T2 from above that she has correctly calculated, squared plus 50 times 1.02 plus an extra 50, and then increased at the end of the month. So that's 50 times 1.002, 50 times 002 squared, plus 50 times 002. You can kind of start to see the pattern. This was the original 50 she put in, compounded for the 3 months. This is the second 50 she put in, compounded for 2 months. This is the 50 she put in this month, compounded only once. Kate uses her method to correctly calculate how much money she can expect to have in her savings account at the end of 10 years. She's using her method, which seems to be a more iterative process. That's quite a unpleasant setup, but you'll notice that each of these terms actually form part of a GP, a geometric progression. So the first term of this geometric progression is going to be the 50 times 1.002, which is £50, 10 pence. And the r, what I'm multiplying by each time to get to my next term, is 1.002. So if I want my amount of money after 10 years, I'm adding up 10 of such terms, and the formula is a r to the power of n minus 1 over r minus 1. And that's in your formula booklet. So typing that carefully into my calculator, to the power of 10. I did write n, I am going to change that over r minus 1. So we're summing 10 terms, so I should have power of 10 here, and that's giving me £505.53. Money, 2dp, as standard. Now, does that seem reasonable? Seems like we're being shafted a bit by the interest rate. In 10 months, I've put in £50 10 times, so I should expect at least 500, and I do have at least 500. The interest rate of 0.2% is incredibly low, so only getting an extra £5.50 seems reasonable. Maybe you can consider that unfair, but it is reasonable. Part B double I. The amount of money in Kate's savings account at the end of 10 years may not be the amount she correctly calculated. Explain why. So, what kind of things could have changed the amount of money in her savings account? Well, the interest rate could have changed, but we've been told what that is. She could change the amount of money she puts in, but we've been told what that is. Now, it doesn't explicitly say that the interest rate is per... Oh, it is. It does say per month. Maybe the most common way that this could be is by rounding. At the end of every month, it's calculated and then rounded, whereas we've used the exact value at the end of every month. So the end of each month may be rounded, and so changing the total subtly. And it will only be a tiny change. Subtly is a really weird word. I highly doubt I spelled that correctly. End of each month might be rounded, so it might not be the exact amount at the end. And all these other reasons. I don't like giving a reason which has been stated in the question. If it states the interest rate is, I don't like giving a reason, well, it might not be what the question said it was. Question 8. A zookeeper is modelling the mass of infant monkeys by that model. Y is the mass in kilograms, X is the age in months, A and B are constants. Zookeeper uses the data to find 2 data points, 3 months to write down that equation, use the other one. So Y is the mass, so for the second one, Y is 12, A plus B log base 10 of the age in months, which is 24. Okay, show that B is that. Well, I'm going to label these equations. Well, that equation 1 and equation 2. Show that B is that. So I need to cancel out A. So let's do equation 2, subtract equation 1. 12 subtract the 6.4 gives me the 5.6. The A's cancel, and then I've got log base 10 of 24, subtract log base 10 of 3 with a B in front of both of those. And when we subtract logs, we divide. So that's the 24 over 3. So therefore B is, as they stated, 5.6 over log base 10 of 8. Find the value of A, give your answer to 2 decimal places. So now let's use one of our 2 formulas. A good tactical hint is to use the one they gave you rather than the one you found yourself, only because if you have made an error, you're not going to use the one with the error in. Double check that I've written that correctly. And B was 5.6 over log base 10 of 8. Now, because we just want to find the value of A to 2dp, I'm not going to do anything fancy. I'm just going to type it into my calculator. So that's a 6.4 subtract log 3 over log 10, which gives me 3.728, etc. Good habit to write out more decimal places than is required and then round afterwards. Again, as many ways as possible to not throw away silly marks because of rounding, etc. Part B, use a suitable value of x to determine whether the model can be used to predict the median mass less than 1 week old. Well, less than 1 week old is saying that my age was the x, a week is roughly a quarter of a month, so let's use x to be a quarter. So then y equals the A, 3.73 plus B, 5.6. Where's the x in the formula? I've lost the x. I'm up here. I was looking in the wrong section. So that's the 3.73 plus B, which was the 5.6 over log base 10 of 8 log x. So that's log base 10 of a quarter. And let's just type that into the calculator and see what happens. We're going to be determining whether this model is valid. So I'm half expecting something to look weird about my answer. My answer might be negative. That will certainly be complete nonsense. And indeed it is. This comes out as negative 0.003. Loads and loads of threes. Which is negative. So model predicts a negative. Y was the median mass. Use a suitable value of x to determine whether the model can be used. So should not be used for monkeys less than a week old. That is just not it's not a good model if you're predicting negative mass. Even predicting zero mass is a little bit suspicious. Moving on to question 9. Find the binomial of expansion of that up to including the x squared. So that's 1 plus n x plus n minus 1 over 2, the x squared. And notice I'm saying x, but the thing in that spot is 3x, so I'm putting in 3x. It does keep going after that. Now just to simplify, is that plus 9x squared? The 2's cancel, the negatives cancel. Indeed it is. Show that the first 3 terms of that binomial expansion form a geometric sequence. Just the first 3 terms. Okay, so we need to rewrite that in a useful manner first. So we're going to write it as 2 minus 3x to negative 1. We need to factor out the 2, which gets hit by the power of -1. And the first three terms, well, I'm going to use what I've already done above. I've already done it with 1 plus 3x. So I'm replacing that with, well, I need to swap the sign, and I need to put in a half in there as well. So I'm really replacing the x with -1/2 x. That's 1 minus 3 lots of -1/2 x plus 9 -1/2 x squared. And you could probably argue that doing that from scratch was easier than trying to adapt part A of the question. It's a good habit to get into, to try and forcibly use previous parts of the question, because they do often, more often than not, help. 9/4 x squared, so that's 1/2 plus 3/4 x plus 9/8 x squared. So what we're trying to show that the first three terms of the binomial expansion form a geometric sequence and state the common ratio. So 1/2, 3/4 x and 9/8 x squared is a GP with first term of 1/2 and my common ratio 3/2x, which is exactly what it wanted. And notice that it said the terms, not the coefficients. So it's important to put that x still in there. I can see that being quite an easy mistake to make. It's given that. Okay, so this is where part A is going to come in. There's the 1 plus 3x on the denominator. It is given that. Find the values of p and q. So the trick with these is to multiply up by the denominator. On the p, the 2 minus 3x cancels. On the q, the 1 plus 3x cancels. And we get that kind of expression. Pick values of x to make things cancel. If we let x be -1/3, that's going to be -12. The p bracket cancels. -1/3 leaves 3q. So q equals -4. I'm going to rewrite that because otherwise I'm not going to see that negative. And just a quick double check that I haven't done anything foolish. And then the second value is when x is 2/3. So that's 24 equals, it's not going to be 3p. Yes, it is. 2/3 of 3 is 2 plus 1, and 2/3 into the q makes it disappear. So p equals 8. It just wanted me to find the values, so I found the values. Q is -4, p is 8. And when you come to check, it's worth putting them back into here and actually combining those fractions together and checking that it does lead to a 36x on the numerator. Using A and B, find the binomial expansion of that. Well, that looks very similar to what I've just done in part B. Notice in part B I had a 36 on top, now I've got a 12 on top. So part B of the question is going to imply that this thing is equal to, well, it's got the third as big as what I've got here. So instead of 8, I'm going to have 8/3, 8/3, and which was the one that was linked with p? P was the 2x minus 3, minus 4/3 of the other one. And now we can use our binomial expansions. If we need to make it really obvious, we can write these with the power -1. And this is where the paper version will be a lot less chaotic. You don't need to swipe backs so frequently. 2 minus 3x was 1/2, 3/4, 9/8. 1/2, 3/4, and 9/8. And the other one was 139. 1 minus 3 plus 9x squared. So now we need to combine them together. We've got half of 8/3 minus 4/3. So that's 4/3 minus 4/3, that cancels out. 8/3 times 3/4 is 2 plus 4, so is that just 6x. 8/3 of 9/8 is 3 minus 12. I'm going to do that in my calculator, trying to keep track of that in my head. Will eventually work, but with a much higher error occurrence. It does give me negative 9x squared. Okay, and that will just keep going. A nice thing to notice is we do miss this constant term, but if we go back to the original, if you sub 0 into that thing, you do get 0. So subbing 0 into the expanded version should also get 0. So it does look weird, but it is expected. The question does keep on going. Find the range of values of x for which that binomial expansion is valid. Only one mark for this. These expansions are valid when the x part is less than the other part. So we need mod 3x is less than 1 and mod 3x is less than 2 from the two separate brackets. Now, of course, being less than 1 is a stronger condition than being less than 2, so I don't need to deal with the second one at all. So it's just that mod x is less than 1/3. The other condition would have been said less than 2/3, but that's guaranteed if you ensure you're less than 1/3. And we finally move away from question 9. That was a long question, lots of parts. Went through a couple of different topics as well. The function f is defined by that. Determine whether the curve with that equation has a point of inflection at 0. Fully justify. Okay, well, point of inflection is a stationary point, so the first thing we need to do is find the derivative. So that's going to be 2x cos differentiates to minus sine. And then if we do f dashed of 0, we do indeed get 0, which means we do have a stationary point at x equals 0. So, well, that doesn't actually tell us anything at all. The point of inflection doesn't have to be a stationary point. But what we do now need is the second derivative. The second derivative is 2 minus 2 cos x. And this is where we have to try and justify. And it's really sneaky because we can see that f double dashed of 0 is 2 minus 2 is indeed 0, but that's not enough. A point of inflection has to have a change of sign of the second derivative. So let's pick something a bit bigger and something a bit smaller. And if this was a point of inflection, these would change their sign. Now, if you're doing this in your calculator, you do need to make sure that you're in radians. Nothing about the question actually said so. But as soon as you see any kind of differentiation, you have to be in radians. So I subbed in 0.1 and I've got that. I've subbed in negative 0.1 and I get exactly the same thing. So there is no change of sign of the second derivative, which implies it is not a point of inflection. Which is, well, not often do they give you these where the answer is no, but it is. And we could, of course, try and work out what type of point of inflection it is, what type of stationary point it is. If we sub a little above and a little below into this one, we will then determine what the gradients are on either side of that stationary point, and then we'll be able to determine if it was a minimum or a maximum. All we've shown here is not a point of inflection. Moving on to question 11. A student states that 3 is the smallest value in that interval. Explain the error. 3 is not in the interval, as 3 is not less than. I should write that the other way around, because we're saying k is greater than 3. 3 is not greater than 3. 3 is not the smallest value in there because it can't be. It's not in there. Student says that there's no smallest value. The teacher gives the following proof. Assume there is, well, there's my contradiction. Let y be that. Well, that's quite interesting because we've got, if we were to imagine a number line, we've got 3, we've picked out some x, and y is then the middle of 3 and x. So step 3, explain the contradiction. Y is in the interval as y is greater than, x is greater than 3, so y is greater than 3. It's greater than 3 plus 3 over 2, so it's greater than 3 still, but is smaller than the assumed smallest x. So we assumed that there was a smallest, we found something that was smaller than it. Well, that's a contradiction to saying the first thing was the smallest. Prove there's no largest value. Okay, this is a really nice question because it's basically written the proof out. It's now asked you to adapt that proof, but in the opposite way. So let's assume, we're going to do it by contradiction again. Assume x is the largest value with 3 less than x is less than k. Let y, well, this time 4's up here, x is here. Let's take y to be the middle, x plus 4 over 2. Then y is less than 4 plus 4 over 2, which equals 4, as the x is less than 4, so y is a larger value in the interval, which is a contradiction because we assumed x was the largest. Therefore, there is no largest value. As soon as we have a largest value, we can find one that's bigger and it breaks. Check that we've done very similar to what the teacher did in part B. Step 1, assume there's the largest value. I wrote it slightly more efficiently than they did, but that's fine. Step 2, pick a clever value. Step 3, do a conclusion. I put a bit more detail in there because part BI told me to do that extra detail. And then step 4, conclusion. I should probably put no largest value in 3 less than k less than 4. Just make it absolutely the same. Guarantee it. And that's the end of the pure section.